TA is.
Oh.
Okay. Are there any questions before we start? I don't hear anything, which means we can continue, I suppose. Well, there are a few things. There are, I think, 2 or 3 things that I want to talk about before we complete chapter 12 on lattice filters. Okay, so one thing I am going to talk about, before I forget, let me just list this: how to expand the numerator in terms of reverse polynomials. So that's one thing I want to talk about. Second thing I want to talk about is the inner product. Without going to proof, we will look at the inner product of the psi and lambda polynomials. So again, without proof, we will briefly talk about them. And the third thing I want to talk about is pipelined lattice IIR filters. Okay, so those are 3 things that I didn't talk about yet. So we'll talk about them, and that will bring us to the end of chapter 12 and really to the end of the content until the midterm exam, but we'll still continue to talk about things, and they may not come in the exam, but that's okay. All right, so these are our topics today, and if there is time, we'll get into other topics. So let me start with the first topic: is how do we expand the numerator polynomial using reverse polynomials. So that's something that I did not talk about. So what are we trying to accomplish? Okay, so if you think about our goal here is to expand. So if you remember, I briefly talked about the fact that the reverse polynomials themselves are not an orthogonal basis set, which means that so we couldn't simply expand the numerator from, if the delay was on the top, then we wouldn't expand using these polynomials, the reverse polynomials. However, once the delay is pushed down, then these polynomials become an orthogonal or orthonormal depending on what kind of polynomial it is, and that becomes an orthogonal basis set, and then we can expand the numerator from these polynomials. Okay, but that process itself isn't trivial. Okay, so that process isn't as trivial. So so we want to expand so the reverse polynomials I equal to 0 to n do not form an orthonormal, well, in this case of E, orthonormal basis set. Okay. However, z to power n minus I phi I star. Okay, so that's if I is equal to So that, let me write down, if I is equal to n, then that's p n star. If I is n minus 1 or n minus 2, if I is equal to 0, then, okay, these do form an orthonormal basis set. Okay, so then we can expand the numerator using these polynomials. So expand n of z in terms of z to power n minus I phi I star z. So that's the expansion of the numerator. So then I can write down the numerator polynomial is equal to some constant di, I equal to 0 to n, times the polynomials z to power n minus I phi I star z. So that's what our goal is. Our goal is to compute di. So that's what we want to do. Okay. So it turns out that it can be, di's can be easily computed by expanding the reverse polynomial of n star in terms of phi. Okay, so what am I trying to say? I am trying to say that in order to compute these d coefficients, we can easily compute the d coefficients by expanding the reverse polynomial of the numerator in terms of the original Sur polynomial phi. Okay, so that may sound like not true. That may sound like not true because it's not clear how this can be possible, but we can spend a little time to show that it is indeed possible. Okay, so let me try to prove that. So I'm trying to prove that, okay, so here is the thing. So n star z, okay, if I compute n star z is equal to summed over all I equal to 0 to n, some constant ci phi I, okay, if I do that, then I guess what we will try to prove is that ci is same as di. Okay, if I expanded the reverse polynomial of the numerator in terms of the original polynomials phi I, then those coefficients ci are identical to the coefficients necessary to expand the numerator in terms of the z to power n minus I phi I star. Okay. Okay, so let's see if we can prove that. So from, if I start from here, so that's what we want. So n of z is equal to, let me just write down phi I star z is equal to okay, so that's this quantity. So from here, if I take the reverse polynomial of each side, So n star z is equal to I equal to 0 to n di z to power minus n plus I. So I am just replacing z. So from here we are taking the reverse polynomial. Okay, so the reverse polynomial n star is equal to z to power n 1 over z. So I should have a term z to power n times everything else that is here, replace z by 1 over z, z to power n minus I minus n plus I, z to power I became minus I, phi I 1 over z, reciprocal of 1 over z is z. Okay, so let's see what we have accomplished so far. So z to power n cancelled out with minus n, z to power I cancelled out with minus I, and we are finally left with this is equal to di phi I z. So that completes the proof that from this equation n star is equal to this quantity. If I had expanded n star using phi I and obtained the coefficient ci, those then must equal di. So that shows ci is equal to di. Okay, that completes the proof of that. Okay, so basically what I guess I am trying to say is that the coefficients expanded from the numerator. So if you look at that example, and here the numerator is expanded using phi 3, phi 2, phi 1, phi 0, and those coefficients are 0029, 00156, 0324, 0215. And if I look at the coefficients at the bottom, they are the same coefficients, and that's not surprising because we just proved that the coefficients that are used to expand the numerator from the modified reverse polynomials are exactly the same as the expanding from the phi polynomials. So still these are same coefficients 0.0029, 0156, 0324 and 0215, so the same coefficients. So that shouldn't be surprising because we just proved that expanding the numerator, using the z to power n minus I phi I, or in this case psi I, because this is the basic lattice filter, those coefficients are identical to the expanding the numerator in terms of just phi functions. Okay, so that's kind of one topic that I wanted to talk about, and that's useful to learn. Okay, any questions before we go to the second topic? Okay, so the second topic that I want to talk about is this, the inner products of the psi and lambda polynomials. So we already know that the phi polynomials, their inner product is 1, and the inner product of phi I phi j is equal to 0 for I not equal to j. Okay. So again, I state that without proof, and I didn't even talk about the formal definitions of inner product. So that we already know. So how can we compute the inner products of the other polynomials, psi polynomials and lambda polynomials? Okay, so let's briefly talk about those two things. that's useful to know. Okay, so what is the process of deriving the psi polynomials, the degree reduction process for psi n minus 1? So if you look at the main difference between the degree reduction steps for the psi polynomial and the phi polynomial. Okay, I have this slide here that shows both of them at same place. Okay, so let's look at that. So the phi polynomial and so if I start with a degree n, initially the denominator is considered the degree n polynomial. So whether it is any kind of lattice filter, it doesn't matter, phi n or psi n or lambda n, for degree n they are all same. Okay, so that's good to know. So then from these you can see that I can write down, okay, psi n is equal to phi n. So for degree n these are same. Psi n minus 1 is equal to phi n minus 1 divided by square root of 1 minus kn squared. Okay, let's try to take a look what I am just saying. I am saying so imagine for degree n, phi and psi are same, they are all same. Okay, so if I have phi n minus 1, in the denominator I introduce another 1 minus square root of another 1 minus kn squared, and square root times square root becomes itself. That becomes the equation for psi. Okay. So once I realize that, I can say that the inner product of psi with respect to itself is equal to 1 over 1 minus kn squared. Okay, so that's why is that? Because the inner product of phi n minus 1 with respect to phi n minus 1 is 1. So the inner product of this with itself is going to be 1 by 1 minus kn squared times the inner product of phi n minus 1 with itself. So that's that inner product. Similarly, psi n minus 2 is going to be phi n minus 2 divided by square root of 1 minus kn squared times square root of 1 minus kn minus 1 squared. So in terms of phi polynomial, I go through one more degree reduction, and when I go through the second step, we need to introduce 1 minus kn minus 1 squared, and then that suggests that the inner product of psi n minus 2 with itself. Again, the numerator inner product of phi n minus 2 with itself is 1 because these are orthonormal, and then you just square these quantities. So this becomes 1 over 1 minus kn squared times 1 minus kn minus 2 squared, n minus 1 squared. Okay. So it's very easy to write down psi n minus 3 inner product will be one more term kn minus 2 squared. And these are the inner products. That means these are going to be the power of those states. So if you were to write down the K matrix for these lattice filters, you can write them down very quickly without computing anything, just based on these inner products. Okay, so that may sound not easy to do, but it is easy to do. So I know that it's not part of your homework for next week, but I'm going to place the midterm exam from last time sometime today. Please feel free to use that for doing the next homework. It's all right, it's perfectly fine, because those were somewhat difficult problems, I think. But it's good to look at those difficult problems and use that knowledge to do the homework as well. So that's perfectly fine with me. So you will see that the questions we're addressing these kinds of things, although not taught in the homework, but still you can see that in the solutions in the midterm sample exam. Okay, so that's good to know. So that's certainly good to know how to compute the inner product without really doing a lot of work, but just by exploiting the knowledge that the phi functions form an orthonormal basis set. Okay, so what about the lambda polynomials? How can we compute the inner products of the lambda polynomials? Again, we have to express those first using the phi polynomials. That's kind of the first step. Okay, so let me just write down here. If I want to write down psi 0 inner product is equal to 1 over 1 minus kn squared up to 1 minus k1 squared. Okay, so that's good to know. All right, so then let's talk about how do we compute the inner products of the lambda functions. All right, so what was the process of deriving the lambda? So so the lambda polynomial is derived by that formula. Okay, so once again at the degree nth stage, we begin with lambda n, basically same as the denominator polynomial, so that doesn't matter. So think about lambda n is same as psi n is same as phi n. Okay, so how can I express lambda n minus 1 how can I express lambda n minus 1 in terms of phi n minus 1? And when I compute that for degree n, these are same, so the numerator will cancel out. Okay, so let's begin with lambda n minus 1 by phi n minus 1 is equal to, okay, so the z to power minus 1 cancels out, the numerator cancels out, and this denominator 1 minus epsilon n kn is in the denominator. Because of that, when I divide by this quantity, this denominator goes to the numerator. So the square root of 1 minus kn squared goes to the numerator. So that's the ratio. Okay, so this is the whole thing is the denominator, and then this goes to the numerator. Okay, so that's good. Okay, that's certainly good. But how can I simplify that further? And of course, if you look at it, it doesn't seem like it's easy to cancel out common terms. But if you remember that epsilon n is plus or minus 1, so I can just multiply epsilon n squared to kn squared. And now in fact I can cancel out square root of 1 minus epsilon n kn, and then in the numerator I am left with 1 plus epsilon n kn, in the denominator 1 minus epsilon n kn, and that whole square root. So that's the ratio. Okay, so once we realize that, so then I can say, okay, lambda n minus 1 is equal to 1 plus epsilon n kn by 1 minus epsilon n kn square root times phi n minus 1. So the inner product of lambda n minus 1 with itself is going to be that inner product with itself is 1. Take the square of this quantity. So that's going to be 1 plus epsilon n kn by 1 minus epsilon n kn. Okay. And without going through one more step, if I skip one more step, I can write down lambda n minus 2 inner product with itself is going to be 1 plus epsilon n kn by 1 minus epsilon n kn times 1 plus epsilon n minus 1 kn minus 1 divided by 1 minus epsilon n minus 1 kn minus 1. So I have skipped a step. Essentially that step would have been lambda n minus 2 is equal to square root of this quantity times square root of that quantity times phi n minus 2, and then taking the inner product and taking the square of this, that inner product is 1, we get that thing. And you can now write down similar expression all the way up to lambda 0, lambda 0. Okay, so that's really how we can compute the inner products of those states, and inner products of those states are the power of those states. So that's the k variable. If you remember the K matrix, those would be the diagonal elements of the K matrix. Okay, so let's see if there was anything more that I wanted to talk about here, but let's take a look at so one technical detail that I didn't talk about. Okay, so we have these inner products, lambda 3, inner product is 1 for that degree 3 polynomial, that's shown here, we talked about that, and lambda 2, lambda 1, lambda 0, 0. Okay, so one thing I didn't talk about yet is how do we choose, I mean we can compute k3, k2, k1, k0 from these polynomials, and that's not an issue, but how do we choose the epsilons, whether they are plus 1 or minus 1? And I haven't talked about that yet. And the way to choose the epsilon, whether it is plus 1 or minus 1, is really chosen in such a way to maximize the power of the state. And so that's kind of the criteria. And if we go through this example here, that's worked out here in example how to select. Okay, so let's take a look what it says here. So the k coefficients k3. So okay, the first thing that we observe is which k magnitude is the maximum value. So if you look at k3, k2, k1 and look at their magnitudes, it turns out that k1 magnitude has the maximum value. Okay. Okay, so one optimization criterion for choosing the sign parameters, so that's the epsilon parameter, is to require that the node associated with the largest k parameter in magnitude have the largest power. Okay, so that's, and then the sign parameters are recursively found by requiring that powers at other nodes be as large as possible without exceeding the maximum value. Okay, so in this case, because k1 magnitude is maximum, and if you look at which of these inner products is associated with k1, and that's this lambda 0, lambda 0. So we assume then that this polynomial inner product of lambda 0 is the maximum. So that means no other inner product can be more than this inner product. Okay, so the way to solve for those sign parameters, the epsilon parameters, so we begin by the inner product of lambda 1 divided by lambda 0, and then you get this quantity, and for that to be less than 1, we need to select epsilon 1 is minus 1. Okay, remember that. So K1 was already negative. K1 is minus 0.97. So if I pick epsilon to be plus 1, then this would be 1 minus minus 0.97, 1.97 divided by 1 minus 0.97, which is 0.03. So this would be 1.97 by 0.03, or about 200 by 3, or 66. And that's going to be more than 1. So the way to make sure this is less than 1 is pick epsilon 1 is minus 1. So that way I get this is 1 minus 1, that's plus 1, times minus 0.97. So that's 0.03 divided by, so this now becomes 1 by 66, which is 3 by 197. Okay. So once we picked that quantity, then, so epsilon 1 is now known. So then compute lambda 2 by lambda 0, and then ask the question, I can compute that quantity here. Then I can ask the question, okay, what should epsilon 2 be, so that this ratio is as large as possible, and you keep going through that process. So that's kind of one technical detail about how to select those sign parameters epsilon for the 1 multiplier lattice, so that epsilon appears in two places, and it's either plus 1 or minus 1. Okay, so I think that is all about the lattice filters that I was going to talk about. And the last thing that I want to talk about is the pipelined lattice, and how do these become pipelined. And that's really okay, so that's the next topic that I am going to talk about. So this was a topic that was of interest to me, and so I asked Jin-Kyun Chung to work on that problem when he came to do his PhD from Korea, and is now professor in Korea. He was Dean of Engineering at Sunbuk School as well. So anyway, his paper, which I found very interesting, and he surely it was very, very impressive. I just asked him to go and look at that problem, and I thought he will come back and tell me after 6 months that it was a difficult problem. But he came back in 3 or 4 weeks and had solved that problem, which is how, of course, not always, but what we expect students to be like. And so, yeah, that was Jin-Kyun's PhD thesis. That's a reference. Let me see if I can find his paper from the list of references. That's reference number 14 at the end of the chapter. Okay, published in Transactions on Signal Processing. So anyway, so it's good to give him credit because he worked hard to solve that problem. And so the first observation is that if the denominator is a polynomial in z to power m. Okay, so if the denominator, So think about the denominator is a polynomial in a z to power m. Then, and this is the observation that Zingyun made, is that then the m minus 1 consecutive k coefficients are 0. Okay, so that's the key observation that he made, and very impressive. And I certainly didn't expect him to work this out so quickly. So once we make that observation, then we can see how easy it is to pipeline lattice digital filters. Okay, so that let's talk about that observation, and then we'll talk about how to pipeline those structures. Okay, so to go through this example, let me start with a very simple example where the denominator, well, think about that as denominator, is something like z to power 4 plus az squared plus b. So of course, in this particular example, m is 2. So a standard polynomial in a z would be some constant plus something times z plus something times z squared plus something times z cube, etc. So here the alternate coefficients are 0, and that means it's a polynomial in z to the power m or z squared. So everything here is z squared, z squared squared, z squared cube, z squared to power 4, and so on. Okay. So if I start with that, and then you can see that the k parameter k4 is going to be the constant term b divided by the coefficient of the highest degree term. So that's b divided by 1, which is b. Okay, once I know k4, then I can reduce the degree. So phi3 is going to be z to power minus 1 times phi4 minus k4 phi4 star divided by 1 minus k4 squared square root. And so if I just substitute, so this is z to power 4 plus az squared plus b minus b times the reverse polynomial is going to be b times z fourth plus az squared plus 1 divided by 1 minus b squared square root. Okay, so that's going to be and then the plus b and minus b cancel out, and that's how we reduce the degree, and then this becomes z to power minus 1 times z to power 4 becomes z cube. Okay, so this is z cube times 1 minus b squared, so these two terms grouped together, 1 minus b squared divided by square root of 1 minus b squared, so that just becomes square root of 1 minus b squared, plus z squared, again if I group these two terms, so this is a minus ab, so a minus ab, so z squared times z to power minus 1 is z, a times 1 minus b divided by 1 minus b squared square root. Okay, so that's the polynomial, and then we can say, okay, so if that is phi3, what is k3? K3 is the constant term, and you can see here that there is no constant term, so the constant term is 0, so this is this thing plus 0 times z squared plus 0, and so that's simply going to be 0 by square root of 1 minus b squared, that coefficient which is 0. Okay, so, and that's the observation. So let's see here. So the property that I was talking about, if the denominator is in polynomial of z to power m, then m minus 1 consecutive k coefficients are 0. So if m is 2, then every alternate k coefficient will be 0. Okay, so if k3 is 0, then I can compute phi 2, which is z to power minus 1 times phi 3 minus k3 phi 3 star by 1 minus k3 square root. Okay, so k3 is 0, so that whole thing disappears. K3 is 0, so k3 squared is 0. 1 minus 0 is 1, square root of 1 is 1. So this then simply becomes z to power minus 1 times phi 3. And all that does is really reduce the degree by 1. So phi 2, to go from phi 3 to phi 2, just multiply z to power minus 1 and then that degree. So this is z squared times 1 minus square root b squared plus, well, if I do a little more simplification and cross out 1 minus b square root with numerator and denominator, then I'm left with a times 1 plus b by 1. No, I crossed out 1 minus b, so 1 minus b left in the denominator, 1 plus b left. Okay, so that's the phi 2. So phi 2 becomes that quantity. And you can see that k2 is going to be a times, okay, so maybe it's easy for me to go back to that constant, a times 1 minus b by 1 minus b squared square root divided by the constant term of the highest degree coefficient, or the highest degree coefficient 1 minus b squared square root. This multiplied by this is 1 minus b squared, and 1 minus b by 1 minus b squared is 1a by 1 plus b. So 1 minus b cancelled out, we get 1 plus b in the denominator. So that's k2. Okay, and then phi 1, so I'm keeping the quantity before simplification. Okay, minus k2 times this quantity times z squared, the reverse polynomial, plus that quantity divided by 1 minus K2 squared square root. Okay. All right. Okay. So we won't work out all the details, but I think what is useful to check, the only thing that's useful to check is that the constant term is cancelled out. And so let's take a quick look at that. Okay. So let's see. We have a times 1 minus b by square root of 1 minus b squared, and then if I multiply this quantity with this quantity, what do we get? So 1 plus b square root, okay, I think let's just write that down. A times 1 minus b by 1 minus b squared square root minus a by 1 plus b times 1 minus b squared square root. So I cross out 1 plus b square root, I'm left with 1 minus b square root and 1 plus b square root here. And I cross out 1 minus b square root, I'm left with 1 minus b and 1 plus b. Okay. And you can see that they are indeed same. So that thing is 0, and that's how the constant term got cancelled out. And then we have something, I'm not going to spend time simplifying z squared quantity, because that's going to be this quantity minus a by 1 plus b times that, all divided by that. So it is sufficient to say that this is something times z. Okay. And now that tells us that k1 equal to 0. Okay, so k1 equal to 0 because there is no constant term. And then phi 0 is simply going to be z to power minus 1 phi 1, which is whatever that quantity was. Okay. So that's the so the whole thing that I guess all I was trying to show you through this example is that if m was 2, then we have k3 equal to 0 and k1 equal to 0, and that's what I was trying to illustrate, that if it is in scattered lookup form, which means it's a polynomial in z to power minus m, not polynomial in z to power m, so it means it contains, so the denominator is something plus or minus, again doesn't matter, some constant times z to power minus m, z to power minus 2m, z to power minus 3m, etc. Okay, so that's what I mean by a polynomial in z to power m. And then consecutive m minus 1 consecutive k coefficients will be 0. If, for example, m was 8, we'll get 1 k coefficient, that's non-zero, then 7 0k coefficients, next one non-zero, then 7 more 0, and the pattern continues. Okay, so that's kind of the first observation. So once we observe that we have this a bunch of k parameters, consecutive parameters that are 0 coefficients, okay, how do we use that information to illustrate the fact that the lattice filters are now pipelined? Okay, so let's talk about that. So it is useful for us to think about how do the stages reduce to something. So if we take the normalized lattice, the basic lattice, or the 1 multiplier lattice, how do those structures reduce to a simplified form when the k coefficients become 0? Okay, so that's what we want to talk about. Okay, so let's start with the first one. So the basic lattice filter basic lattice filter, sometimes called the Gray-Markell lattice filter, which is okay. So that is the basic lattice filter. This is minus Ki and plus Ki. So if K is 0, then this multiplication by this quantity is 0, then nothing is being added, so that edge disappears. So something plus 0 is itself, and that multiplied by 0 means nothing is being added here. So what we are left with looks something like that. So if the K coefficient is 0, then that's the stage just reduces to that. So it's simply all these things go away, all the computations go away, so we only get one delay element. So for example, if we had some denominator d of z is some coefficient times z to power 8 plus some coefficient times z to power 4 plus some constant, then what really would happen, so we would, of course, the first k coefficient, k8, would be non-zero. And then that's for K7 equal to 0, then K6 equal to 0, and then K5 equal to 0, and then we have K4, which is non-zero, I'm not going to write this down, but basically this will be 4 delays. Okay. So what you see here is the z to power minus 1. So these all these things, these are now 4 delays, and that's exactly what I wrote down here, because we would have K3, K2, K1 would be 0. We would have 1 delay as part of that stage, plus 3 more delays as part of the 3 stages with 0 K coefficients. And that's what we mean by the pipeline lattice filter. And you may think that, well, okay, I mean, the filter itself is probably not pipelined yet because we haven't retimed the delays to distribute them, which you need to do, and that's really something some of you have struggled with in the last year spring class, how to take these delays and redistribute them so that we can meet the iteration period bound. So if you think about what was the iteration period bound in the original filter, so in the original filter, we would, so if there was one more stage, then the iteration period bound in the original lattice is that loop here. So you go through 1 multiply, 1 add, 1 delay, some other add operation, and multiply and add. So that's so the iteration bound is 2 multiply 3 add, I believe, right, divided by 1. And if you look at the pipeline filter, the computation of the loop still remains the same, but the number of delays has gone up by factor 4, and that means the iteration bound or the loop bound has come down by factor 4. And so we won't bother about how to redistribute the delays, but it could be done, and then it could be shown that the multiply add operations could be fine-grained pipelined by redistributing these delays. Okay, so some of you have struggled with these kinds of things, never really thought about how those problems were created or where they came from. Now may be able to relate to those things. Okay, so if you ever wondered where these kinds of structures came from, so you can now see their origin. Okay, any questions about this pipelining the lattice or increasing the number of delays in the loops in the lattice filter? Yeah.
I guess this looks really similar to like interleaving by 4 in this case.
Okay, Joe's point is well taken that it looks like all we have done is we have replaced the delay by 4 delays. And okay, so what is the big difference between, okay, that's a good point. I mean, so if we took that structure and interleave by factor m or 4 in this example, then I would get that structure. Okay, I would get that structure. Okay, so first of all, here's the thing. If I had a structure like that and I wanted to get to a structure like this, first thing I would need to do is to use these k coefficients to get a denominator, then apply scattered lookup pipelining to get another equivalent denominator, then from that get this. So these k coefficients have nothing to do with the original transfer function. Okay, so this is a completely, it's equivalent but a different transfer function. That's the first difference. Second difference, if I am processing one time series, let's say the input time series x, we are computing y, so this is taking the sample numbers x0, x1, x2, x3, etc. If I took that original one here and interleaved, then we would take x0, x0 prime, x0 double prime, x0 triple prime, then x1, x1 prime, etc. So we would be interleaving 4 different time series through that hardware path. Of course, then we delay that, replace that one delay by 4 delays. And yes, replacing one delay by 4 delays would help us to reduce the critical path. So if indeed the critical path was t, and let's say that I'm able to reduce that to t by 4, then the original time period would be 0, and then if I was able to reduce that to t by 4, then the next one would be t by 4 and so on. So this would be t. So as you can imagine, and as the time period, so the clock period or time period, so if the clock period here was t or the critical path was t, and I pipelined by interleaving by factor 4 and retimed, and so the sample period is still t, so the sample period does not change. I just take 4 different time series. I am not increasing the sample period, whereas here the sample period is exactly t by 4. So we are processing one time series, not 4, and at 4 times sample speed and not 1 time sample speed. So those are the 2 fundamental differences. Very important to understand these differences though. They can be somewhat technical and subtle. They look very similar, they look deceptively similar, but very different. Okay. But these, I just didn't replace this delay by 4 delays to get to that point. I took that transfer function, applied the lookup, scattered lookup pipelining, got a different denominator, then got to that point. Okay, so let's just take a quick look about the other two structures. So let's take a look at the normalized lattice. And if you look at that normalized lattice, so again, if k is equal to 0, so there is nothing being multiplied, so that quantity is 0 times something. I'm not adding anything anymore. Nothing being multiplied here. K squared is 0, 1 minus 0 is 1, square root is 1, so that path goes itself. So we have, so essentially that path going forward, that path going backward, and then a delay. So once again, same kind of stage as the basic lattice. If k is equal to 0 for the normalized or the scaled normalized, again everything remains the same except the there is an increase in the delay. So k minus 1, m minus 1 k consecutive, m minus 1 consecutive k coefficients are 0. So you would have z to power minus 1 for one non-zero stage like this, and then m minus 1 consecutive delays, so they group them together, that's m delays. Okay, so it's another matter to pipeline those things, but at least we have been able to keep the loop computation the same, and we have been able to increase the number of delays by factor n in each and every loop. Okay, so if I just go through quickly the last structure, okay, so so if we take that structure and substitute k equal to 0, okay, so okay, so let's take a look what we see here. So so k, okay, this quantity is 0, k is equal to 0. Okay, so if this quantity is 0, whatever that sum was, we don't need to worry about that. Okay, don't worry about what was this quantity minus epsilon n times that quantity. Okay, that it was something, and then times 0. Okay, and then that 0 is fanned out here, so I'm adding 0 to that. 0 times plus or minus 1 is 0, so that's 0, and then plus that quantity, 0 plus that quantity is itself. So at least in the numerator, in the top path, you can see that so this sum being some finite sum has a zero effect because that's multiplied by 0 and then multiplied by 0 multiplied by plus or minus 1 and added to itself. So that's the quantity. So ultimately this is the only path that survives. That path does not survive. So we start with the input and go here and the delay. Now what about the backward path? Now when we come to the backward path, all I need to worry about is going back this way. I'm taking this input and add 0 to that because this 0 times something is 0 and you add 0 and really nothing happens. Okay, so that's how it reduces to again same kind of structure where we have no computation but just a delay for that stage. Okay, so that is how all the different lattice structures simplify to just one delay without any computations. And then we would have m delays grouped together. Okay, so let's see if we can take a quick look through some of the examples. Let's see, it says take this transfer function. So looks like so every alternate k coefficient should be 0 because it's a polynomial in z squared. And let's see what it says here. So k coefficients, alternate k coefficients are 0 and pipelined basic filter. So that's the 0 coefficient, just a delay. 0 coefficient, just a delay. By the way, the numerator still has to be expanded with respect to all these polynomials. Okay, that's something to keep in mind. So the numerator is indeed expanded, even though this was a 0 k coefficient, but still has to be expanded here and here. Okay, so for the 1 multiplier, again same kind of structure. There is just no, that's not true. This is not true because this is just not pipelined yet. This is second order, so that's not pipelined yet. Let's see if there are other examples. Four-level pipelined normalized lattice. So this one is normalized lattice again. So it threw out the path going down and the reverse polynomial going to the left, that we threw out because the output is, it's an pole 0 filter, so the 0 is expanded. 0 is expanded from all these polynomials here. Let's see, it looks like degree 8. So if you start with phi8, phi7, 6, 5, 4, 3, 2, 1, 0. And the numerator is expanded with respect to all of those phi coefficients. K, 7, 6, 5 are 0, so those computations are gone. We just have delays, and same here, okay, are gone. K coefficients K3, K2, K1 are 0. And yeah, there is a little example showing how those delays are distributed. If you look at the loop here, that has 4 delays, and another loop has 4 delays, and the long outer loop has 8 delays. And one way to quickly check is if the pipelining is correct or not. So if you look at the number of delays in that inner loop, 1, 2, 3, 4. And if you go to the outer loop, 1, 2, 3, 4, 5, 6, 7, 8. So something is correct. And you go through that loop here, that should still be 4, 1, 2, 3, 4. So that's how, at least again, without bothering about how it was retimed, that can be a tedious process. At least you can see that that does satisfy the pipelining property. Okay, so any questions about pipelined lattice IIR filters. So if you think about the typical signal processing functions, we have talked about IIR filters, FIR, FFTs, and those kinds of things. And so we just have a few minutes left, and maybe without diving into detail, I can just maybe talk briefly about how can we use these kinds of ideas. So by the way, if I am going to teach anymore, I may just quickly glance over things as opposed to working them out in detail, because there will be no more homework from whatever I teach. So if you think about the other important operation in signal processing is the so-called least mean squared adaptive filter, and a lot of the filters are adapted based on channel conditions, and that's really what you learn. And if you take a class like adaptive filters, you are always learning how the cell phone is changing the filters based on the channel variations. So you are moving away from the base station or close to base station, and then the channel is changing. Or we are sending data through the cable or fiber cables or coax cables. And again, depending on the noise conditions, there is of course attenuation, but those coefficients are always changing. So a class like adaptive filter will teach about a lot of different kinds of adaptive filters. But the least mean squared adaptive filter, the so-called Woodrow-Hoff filter by Bernard Woodrow, who was professor at Stanford and still is emeritus. So this is Woodrow and his student Hoff. So they invented the LMS adaptive filter, and it's still the workhorse of all adaptive filters, Woodrow-Hoff filter. There's a small derivation here. If we have the input process UN and we filter that with the weight parameters W, then that inner product W transpose U is the estimate of the desired signal D hat. Okay, and then the error signal En is the desired signal minus its estimate D hat N, and so the way to adapt the coefficients is to compute the gradient of the squared error with respect to the W transpose and set that equal to 0, and solve for so the gradient of the E squared N with respect to W transpose is this quantity minus 2 times error times the input U. Okay, so then the weight update Wn is the previous weight minus half times the learning rate mu times that gradient, which is minus 2 times E times U, and then that's the standard LMS equation. Wn is Wn minus 1 plus mu times E times U. Okay, so what is the fundamental bottleneck here? So that's the filter block where we are taking these weights W at time step n minus 1, W1, W2 up to Wn. These are the n taps. We adapt these weights based on the gradient computation. So we compute the gradient D minus the D hat, that's the error, multiply by mu, multiply by the input U, so U and UN minus 1, UN minus 2, etc. And multiply that and feed that to that adder, and that's the weight update. So that's the typical block diagram of the LMS adaptive filter. And so one goal is to pipeline that LMS adaptive filter. And how can we pipeline that LMS adaptive filter? And so pipelining, so there was work based on so-called a delayed gradient. Okay, so if we start with the section 10.8, pipelining these adaptive digital filters. So the first thing that we can do, okay, so I have run out of time, so maybe I'll quickly go through this next class, and then we'll jump into more complex adaptive filters, namely decision feedback equalizers and how those could be pipelined. We'll talk about that next class. So again, as I indicated, you won't be able to appreciate a lot because unless we really go through them in detail, of course, it's hard to appreciate it, but that's the nature of the things. This is the first time that I have talked about these in this great depth. The class always had project, so whatever I taught in the last part, we wouldn't have homework or we wouldn't have detailed understanding of things. That's the nature of this kind of class. But this is the first time that we have no project and students are working out detailed problems all the way through the end. So, of course, I'm not sure what's good or bad. I think there is good or bad in everything. Nothing is either good or bad. So, but anyway, I'm happy that we went through this exercise. So, see you next class. I am certainly happy to hear your thought about it. It was good to have not the last 4 weeks of homework, but go over very quickly on different topics. Would that be attractive to you? That's how we have done this last time.
Yeah, well, I feel like I haven't looked at it yet. Or